in x. So that means the flow is uniform. All quantities are uniform in x. Okay, that's all you had to write. After which you can you apply the continuity equation and you show that since this is 0, so v is a constant, and at 0 and h or plus minus h by 2 whatever, v is 0, v is a constant, it is 0 on the wall, so it is 0 everywhere. That's all you had to write. In okay, so that is very important. This is the only this is all the solution required for quiz 2 problem 2 part 1. Okay, that's all you have to write. Don't have to write stories. Okay, so same things, similar things will appear in your midterm exam also. So please be prepared for questions which you obviously have not seen, but you might have seen their cousins in the class or the practice sheet or the notes. Okay, I'm not going to give you something completely new, of course, but you would have seen something like that in the class. Okay, and I hope you guys are okay with it, because in past one session was not okay with me giving questions which haven't been solved in the lectures. I don't understand what's the point of an exam in that. Okay, so, and the other thing is, me giving these kind of exams is not a taunt to you. Some people take it personally and say like, oh, you are you are being arrogant about by giving these questions. No, I'm not trying to do that. I'm trying to induce thinking in you guys. Okay, that's my aim. My aim is to teach you how to and when to start thinking. Okay, instead of just rote learning and usually what happens in courses here, you need to start thinking and applying it. And believe me, right now you feel, oh, why are you giving us these kind of questions? But throughout the course, if you are able to solve, so there are going to be 7 quizzes, there are going to be 2 major 2 big exams. If one problem you are able to solve completely, no, it will boost your confidence. Okay, it will boost your confidence to a level where all after that you will be able to solve most of the problems later on. Okay, so the aim is not to taunt you guys, but the aim is to give you a lot of chances so that you can start solving questions. Okay, so I hope that's enough pep talk for midterm. Okay, so let's get back to our discussion on Stokes flow. So today we'll look at Stokes flow, we'll end the discussion on sphere, and we'll try to end the discussion on lubrication theory as well, because I do want to cover that in the midterm. So, so far what we have done is we have solved for Stokes flow or low Reynolds number flow past a sphere. So what we did was if you look at the beginning of the previous discussion, you will see that we started with the dimensionless Navier-Stokes equation. So there is an unsteady term also. So we are always considering that initially only we are imposing that the flow is steady. Okay, there is an unsteady term as well, and I am simply ignoring it. Okay, I am simply ignoring the unsteady term. Now the idea here is that if you look at this equation, okay, then we chose that L is equal to the radius of the sphere, and then you will get the equation that Re corresponding to the radius u star dot del star u star equals, and the other thing that we chose was for P naught, we chose the scale as mu u naught over L. So once you do that, this will be sorry, this to be an L. So this and this will be same, and they can be combined into the Reynolds number, and then you will get minus del star P star plus del star square u star. Okay. Now we were doing all of this analysis in the limit Re much less than 1. Okay, the solution that we evaluated yesterday was in the limit when Re corresponding to the radius is much less than 1. Okay, now there is no reason for the length scale to be of the order radius. There is no reason for the length scale to be of the order radius. Suppose we are looking at the flow field very far away from the sphere, but still not at small r tends to infinity. Okay, we are far away from the sphere, but we are still not far away enough that we can say that r is tending to infinity. Now this should start some questions in your head, that what do you mean by this? Because if you are far away from the sphere, isn't that what we label as, okay, r tends to infinity? And that's where the crux of most of this course actually is hidden, that there are asymptotic limits where you can find yourself between r tends to infinity, but still when small r is much greater than capital R, there are places where these restrictions will hold. And so what I say is, instead of putting L as capital R, what if I put L as capital R by Reynolds number? What if the length scale that I put is capital R by Reynolds number? The moment you do that, you will have, so if you look at this equation, you can cancel out L from here, and your L is capital R by Reynolds number. Okay. So what would that become? So if you look at this equation, it will be u naught square u star dot del star u star. Substitute this for P naught, you will have nu u naught over L minus del star P star plus del star square u star. And now if you substitute this for L, so this is R, okay. Now what is this? U naught square R by nu u naught is simply u naught R by nu, which is what? Which is what? The Reynolds number. If I take this side, then the equation that I get is simply RER this is very different from this, and the two equations were derived by changing the definition of my length scale. Okay, the two equations were derived by changing the definition of the length scale, and now you see essentially what is this equation communicating to you? So if this equation was communicating that the inertial term on the left hand side, because it is getting multiplied by a very small number, and assuming that a non-dimensionalization is fine, so this guy, the starred quantities are all order 1, then we said that inertial terms are much smaller than these two terms. That is what we had said in the Stokes flow equation derivation. But now what do you see? What you see is that all terms are of similar orders of magnitude. What you see is that all terms are of similar orders of magnitude. All terms are being multiplied by the Reynolds number. So essentially the equation is this. Essentially the equation is this. Okay, and this introduces a concept for us which we are going to look at even more deeply as we go towards boundary layer theory, and that is asymptotic matching between near field and far field. Basically what this length scale is telling you is that there is a far field, where the radial distance is of the order, or the radial distance scales as r by Reynolds number. Okay, there is a near field where the radial distance scales as the radius. For example, if the sphere has a radius of 1 centimeter, then you are 5 centimeters, 4 centimeters, 7 centimeters away from the sphere, center of the sphere. 10 centimeters away from the center of the sphere. Okay, yeah.
How did we choose Reynolds number? Why didn't we choose the scalar r by Euler number or some other dimension? R by Reynolds number.
Because we are doing all of this in the limit RER much less than 1. So we didn't choose. So the choice is not governed by any scientific fact. Choice is our choice. What I'm trying to say is this is what happened when L was R. When L, basically L being R means the length scales are similar to the radius of the sphere. Then what I am saying is, what if the length scales are much larger than the radius?
Because you are claiming that at some far field, this may be the length scale, right?
I am saying far field is defined by this. I am saying that if I choose this, then this happens. If you remember, then Euler number is essentially what was Euler number? Euler number is P naught over rho U naught square. And if you choose this as P naught, if you choose this as P naught, then this will also turn out to be 1 by RE. So you can write it like R times Euler number also. It's okay, because the pressure scale is related to viscous stresses anyways in this question. So the idea is that if I choose this as the length scale, then all terms in the equation are of similar order of magnitude. And the intuition is that, let us say you have a flow going past the sphere. If you zoom out enough, then that sphere is basically a point. If you zoom out enough, then the sphere is basically a point. So any change in the flow field due to the sphere is very negligible as you move away from the sphere. Okay, let us say I had a spherical pollen in this room, and there was a flow, very low Reynolds number flow happening over that spherical pollen. And I see that pollen as a point. There is some deflection of the flow due to that point. And what this equation is saying is that the deflection is so small that all terms turn out to be equally small. Here what we are saying is that the inertial term is small compared to the viscous and the pressure terms. Very close to the sphere, due to the no slip boundary condition, you have very high viscous stresses compared to the inertial terms. But as you move far away from the sphere, so far away that that sphere is basically a point, in that case the viscous stresses are as small as the inertial terms, and that is why all terms are basically of the same order of magnitude in the far field.
Basically, we've taken the length scale independent of the object, right?
Not independent of the object, this is another length scale that I can define, and it is dependent on the radius. But what I am saying is that radius has been shrinked.
RE is also dependent on the radius, it cancels out.
You can think of it like that, but in this problem, yeah, that's what happens. Okay, but what I'm trying to, there could have been another dimensionless number which may not have length scale in it. Okay, so it looks like here, as you said, but that is not the case. What I'm trying to say is, if your length scale is of order radius, then this is what happens. If your length scale is much bigger than the radius, then these are the governing equations. Okay, and what this tells us, that in the near field you have the Stokes equation applied, and this equation is usually called, it's not technically what was derived by Oseen, but we are going to call it in this course as Oseen's equation. In the far field we have the Oseen's equation applied.
We're able to take this because in the limit of far field, since Reynolds number is much less than 1, the length scale becomes infinity.
No, the length scale doesn't become infinity, the length scale becomes much larger than the radius. That's what I'm trying to say. Asymptotics helps us to differentiate between infinity and a length scale much larger than another length scale. Okay, the length scale here is larger than the radius, that's all you have to say. It's still not tending to infinity. Okay, and the idea here is that far away from the sphere, when you're far away from the sphere, if you remember when we were deriving the Stokes flow equations, Stokes flow solutions, What was the faraway boundary condition that we put? What was the faraway boundary condition that we put? We had said that it's basically the velocity is u naught I cap. That is what we had used. Okay. And now what we are saying is technically that is not correct, because technically far away from the sphere this equation doesn't even apply. Okay. And flow past a sphere is a very special case when you can apply that boundary condition and still obtain a solution of the Stokes flow. If you try to do the same thing for flow past a cylinder, there is no solution that you will be able to find when you apply the faraway boundary condition to the Stokes flow equation. You will have to consider this. So basically cylinder is a much more difficult case than a sphere. For probably the first time and last time in fluid mechanics, cylinder is a much more difficult case than sphere, because what you will see is there is no solution possible to this equation when we apply the boundary condition to infinity. It just so happens that with sphere we can do that. Okay. So technically what we did was not fully correct. What we did was we applied the infinity boundary condition to the solution for this equation when we should have considered this guy. Okay. On top of this, what I am going to say is for sphere what we did was correct, because as it happens in far field, if flow is uniform, basically u equals u naught I cap at leading order. Okay, at leading order, if flow is uniform, then Osin's equation is also satisfied. So technically what happened with sphere was we got lucky, and without considering Osin's equation we found a solution. And if you look at your stream function, what was the stream function? What did we have for the stream function? What was inside? So there was this sine square theta, huh? Small r by 4r, capital R by small r. In the limit, so from here you can find u theta and u r, and we said that in limit r tends to infinity, these guys were tending to. So if you look at u theta, what was u theta that we had derived? So u theta was minus u naught sine theta. What was inside for u theta? Hmm? We had this yesterday also, right? 1 minus uh-huh. Hmm? Okay, and here 1. Now what you see here is that in the limit r tends to infinity, technically these terms are not 0, but they are approaching 0. Okay. If you compute, so using this u theta and u r, let us compute what your u dot grad u looks like. Okay. So u dot grad u is defined as u r del by del r plus u theta by r del by del theta of u. Okay. And if you compute this, you will see, so for example, if we take the e hat r component of this term, so this is a vector, if we take the e hat r component of this term, you will see it is u r del u r by del r plus u theta over r del u r over del theta minus u theta square over r. Notice how this comes, because when you represent this as u r e hat r plus u theta e hat theta, don't forget that E hat r and E hat theta are varying with theta. So, when you do the differentiation inside and take the E hat r component after that, you will get this. That is how you will get this term. Okay, so be careful with this. So, if you compute this, it will turn out to be something like, so this term will come, I mean I am not doing the full algebra here, you can do that back home. I am just writing the final result. There will be other terms also, and what you will see is that this term will have an order of magnitude, and the order of magnitude of this term will be, so u naught square. So, what is the leading order term that you will get from here? Here there is a 1 and there is a 1 by r square. So, actually the scale of this u dot grad u will come out to be u naught square capital R by small r square. The scale of u dot grad u will come out to be this. Okay, and the scale of, let us say, nu del square u is something that we know, we have already derived that, we have already derived pressure gradient on all those terms, and the scale of this term is simply nu u naught capital R over small r cube. So, let us divide them and see what we get. Nu del square u scaling over u dot grad u scale is basically, so u naught, one u naught cancels out, capital R cancels out, and what do we get? So, r square, we get nu over u naught capital R by small r. What is this quantity? Nu by u naught capital R is 1 by RER. The other way to look at it is, the other way to look at this is basically the scale of u dot grad u over the scale of nu del square u is small r by capital R times Reynolds number. So, what this is saying is you can ignore this term. So, this term can be ignored with respect to this if small r by capital R times the Reynolds number is much less than 1. Only then you can ignore the inertial terms if small r by capital R times the Reynolds number is much less than 1. And this should tell you that why I picked this as the choice, the capital R by RER. What this is saying is there are two non-dimensional parameters actually in our problem. One is small r by capital R and the other is the Reynolds number. And I'm saying that I'm solving everything in the limit of this Reynolds number going to 0, or I'm solving everything when the Reynolds number is very small. But even if Reynolds number is very small, this number will not always be small. If my Reynolds number is, let us say, 10 to the power minus 2, then I could be 100 times radius away from the sphere, and then r, small r by capital R times Reynolds number will be order 1, not much smaller than 1. Okay, 100 times radius away is still not infinity. There is still 1000 times radius away from the sphere. Okay, so this should give you an intuition. There is a place between infinity and the near field, and that is the far field that we are talking, and in that far field these terms are of similar order of magnitude. Why this is required is because whatever we have found for the Stokes flow solution, whatever we have found is correct at the leading order. This discussion is important when you have to find higher order corrections in that term. For example, there are higher order corrections in the Stokes flow drag, the 6 pi u naught mu r that we derived yesterday. There are higher order Reynolds number corrections that you can find. Okay, there are further corrections to the force, drag force, that you can find. So 6 pi u naught r mu plus something times the Reynolds number plus something times Reynolds number square plus so on and so forth. You can find these corrections, but to find these corrections, this distinction between near field and far field becomes important. Now, where does this word asymptotic matching comes into picture? What we say is there are two coordinates, one is r and the other one I define is, let us say, xi, and I define this xi as small r by small r times Reynolds number r. So there are two coordinates that we define, small r and xi, and I solve the fields as a function of small r comma theta here in the near field. I find the functions of the field as xi comma theta in the far field, and I try to asymptotically match them here. And the way we match is that whatever you have in the near field, let's call it psi near field, we say that this guy for r tends to infinity comma theta should be equal to psi far field, let's say f xi tends to 0 comma theta. And this is how your asymptotic matching looks like. This is something that we will cover when we look at inviscid flow and boundary layer theory. Okay, as it turns out, for any flow, yeah, xi is tending to 0. Xi is tending to 0. So I'm looking at a very small xi. That doesn't need to mean that r is small. So I have rescaled the coordinates. What I have done is basically I have zoomed out enough for the far field. I have zoomed out enough and I am looking at a very small radial distance in this zoomed out picture. That is why it is asymptotic matching. That a very small distance in the zoomed out picture and a very large distance in the zoomed in picture, I am equating those two.
You said that in the far field,
Hmm.
these two terms will be similar.
Yeah.
But then you proved that in the far field they are not similar.
No, they are right. The scale of these two terms in the far field, when small r by capital R is, let us say, 1 by Reynolds number, which is large, then this ratio of scales is 1, right?
But then you've written that it's much less than one.
No, if this is much less than 1, then this is much smaller than this. However, if similar to 1, then the scales are similar. So this is near field, this is far field. Okay, yeah.
Say that for spherical coordinates we did not actually make a mistake, and when we did.
Because what happens is that if you try to solve this Oseen's equation, okay, at the leading order, you will get what Stokes flow solution gave you, which was the uniform flow. So basically what I'm trying to say is uniform flow also satisfies this equation. All terms are 0. Okay, uniform flow also satisfies this equation. All terms are 0. So at order 1, so if you recall, then our Stokes flow did not have any Reynolds number into it. Okay, it was simply this guy. So there was no Reynolds number correction. If you recall, how did we formulate the Stokes flow equation? So there is RER here, then we do the asymptotic expansion and we are considering only the leading order terms. If you consider the leading order terms here, you will get the uniform flow solution. So for sphere, we actually didn't make any problem, we just got lucky. But for cylinder, things are not so good, and you have to consider the leading order solution from the Oseen's equation as well and find further order corrections. And then we do this when we match the two solutions. And this is something that we are going to do very often when we look at boundary layer theory and inviscid flow. Actually, inviscid flow, there is no inviscid flow in reality. As long as you are not considering super cooled super fluid helium, which is very close to 0 Kelvin temperature, which is known to have no viscosity. As long as we are looking at engineering flows, there is no fluid which has zero viscosity. So, there is no flow which is technically inviscid. There is only a possibility of inviscid flow approximation to a real engineering flow. And as it turns out, inviscid flows are simply far fields of fluid flows, and boundary layers are near fields of fluid flows. Okay, and in the limit of large Reynolds number, that's how the distinction we can, that's the distinction we can make. Okay, we'll do this more thoroughly after midterms. But this is just a basically what the take home from our discussion for now should be that Stokes flow is not the end of lower Reynolds number flows. For higher order corrections, if you want to find, you have to look at the Osin's equation and how this procedure is done. Okay, when I upload the notes of this chapter, I'll give you some details and I'll cite the paper from where you can read these things. But yeah, these things are very important. Okay, so for example, so this is like a very interesting fable where there was a scientist who was trying to calculate higher order corrections just from Stokes flow equation, and he just couldn't find it. You can try it yourself, and what you will see is, let's say we were trying to solve, if you recall, we had made the expansion like this, right? And then u was u naught plus re u1 plus so on. Okay, essentially what we had done was we had you can write this as psi naught plus re psi 1 plus so on. There was a scientist who was trying to find psi 1 through this equation. He couldn't find, he could not impose the boundary conditions, and he just left mathematics altogether. He turned to philosophy, and this is usually called the Whitehead's paradox. And of course there's no paradox, it's just that these guys didn't know about asymptotic matching. This theory was formulated around 1940s 50s, around World War II. Then most of the fluid dynamics, the modern day fluid dynamics developments were made. In fact, the boundary layer theory was unknown before Germans were interested in high speed flight and bombs and so on and so forth. Nazis, not all Germans. So we have a lot of Nazis to thank for these theories. Okay. All right. So this closes our discussion on this flow past a sphere. And what we are going to consider now is another case where we can apply the low Reynolds number assumptions, and that is the lubrication theory. And lubrication theory is the first example where we start to consider. So, if you recall how we have been taking the length scale to be same in all directions. Whenever we consider dimensionless Navier-Stokes equations, we have been taking length scale to be same in all directions. Lubrication theory is the first place where we will break that habit and try to consider different length scales in different directions, and that is important from the setup of the problem. And the idea of lubrication theory is that, let us say there is a channel or a slot. Whenever I say it's a slot, it's like a, you should imagine a channel. So channel meaning in the z direction everything is uniform, you may consider it to be infinity. In the z direction, in the xy direction there is some flow happening, so it's all planar. The moment I say channel in this course, you should imagine a planar flow, a 2D planar flow. Okay, so let us say there is a channel, and this is x and this is y, and the height of this channel is h of x, and of course there is a x direction velocity u, y direction velocity v. Now what we say is that this hx, so the hx changes over a length scale of L. So the x length scale is some L, and let us say h is equal to h naught at some length, at some distance, and the y length scale we say is h naught, and the whole problem is set up in the limit when epsilon h, which is defined as h naught over L, is much less than 1. So what we are trying to do is we are trying to simplify the governing equations, we are trying to simplify the Navier-Stokes equations in this limit. That is, when flow is happening, flow could be happening in both the directions, and in fact we will see that flow is not technically uh, flow is not completely unidirectional in these kind of cases. At the leading order you can consider flow to be unidirectional, and what we are interested in is if this is the case, then what are the flow rates, or given a pressure drop how much flow rate can I obtain in this kind of a situation. Okay, so that is the essence of this problem. Basically we are trying to solve for flow given some boundary conditions, and now the x direction velocity scale I will pick as some u naught. This is some u naught. Okay, I don't know what this u naught is going to be, and y direction velocity scale I'll pick as some v naught. And for now let us ignore pressure scales and everything, and let us just focus our attention on the continuity equation. So continuity equation is del u by del x plus del v by del y equals 0. When we non dimensionalize this we will simply get u naught over L del u by del x plus v naught over h naught del v by del y equals 0. So there are stars of course for dimensionless variables, which means so this is what we get for the dimensionless continuity equation. This is what we can get for the dimensionless continuity equation. And now we have to think, what does this equation communicate about the scales of the velocity? So these things are fixed by the geometry of the problem. Okay, L and h naught, they can be fixed by geometry of the problem. Okay, for let us say some length some velocity scale u naught in the x direction, we can say something about the scale of v naught from here, or we can say something about the scale v naught from here, and the idea is for del u star by del x star and del v star over del y star to balance each other, v naught over u naught should be equal to h naught over L. This may look like, okay, you are going in circular direction because you want both of these terms, so you are picking a scale of v naught, but there is a physical way of justifying why the scale of v naught is this. Basically, why would there be any y direction velocity in this case? Why would there be any y direction velocity in this case? Let's say the channel's height is varying like this, why would there be any y direction velocity? Let us say the flow is coming onto this channel from here, then the moment it sees some deflection in the wall, it will turn according to the wall, right? The flow will simply try to turn according to the wall here and here locally. Okay, now if there is a flow that is coming onto straight where y direction velocity is 0 and it turns only slightly due to the deflection in the wall, how will you compute the y direction velocity? How will you say what is the y direction velocity? The flow has slightly turned. So the angle with which the flow has turned is some theta, which is very small. What is that angle that that flow has turned? So this theta will be approximately equal to dy by dx or dh by dx, right? Tan theta is almost theta for small angles. So the flow deflection, if it's coming like this, it has deflected only so slightly like this. So if the speed is maintained as constant, what is the y direction velocity? U tan theta, u sin theta or u tan theta, whichever one you want to say, right? And if the speed is maintained as or x direction velocity is u naught, then y direction velocity comes out to be. So if there is a flow that is at an angle, very small angle theta, and this is v naught, and this is how we have defined u naught, then we know v naught is u naught tan theta, which is approximately u naught theta or dh over dx, which is basically u naught h naught over L. That's how we have picked the length scales. So if the flow turns ever so slightly near the wall due to the wall, the angle of the deflection is very small, and the angle is given by h naught over L, and that's why v naught over u naught should be h naught over L. Okay, this may look like a circular argument where you want something, so that's why you're picking a length scale, but actually a true length scale for v naught is this only. From the physics, from basic intuition, you can derive that. Okay, so once you pick this as the scale of velocity in y direction, then we get that the non-dimensional continuity equation is simply this guy. So nothing changes. Instead of saying that del u star by del x star is 0, okay, because del u star by del x star, if you say it's 0, then what you will derive is that at the leading order, also there is no change in velocity in the x direction, which is not what we want. Okay, but again that is also a circular argument. The true flow of information should be you going through this and then considering this physical picture and then reaching this. These are simply consequences of picking this length scale, oh, velocity scale. Now let us non-dimensionalize the y momentum equation and see what we get from there. So let us non-dimensionalize the y momentum equation. So we are always considering steady flow, by the way. For now, we are considering steady flow. We may look at some unsteady cases later on. So we are looking at u del v over del x. This is our y momentum equation. Let us start non-dimensionalizing this. This is u naught v naught over L u star del v star over del x star plus v naught square over h naught v star del v star over del y star equals minus p naught, some scale for p naught pressure, which we are picking as p naught, and then nu times v naught. So what I'm going to write here is h naught square and then h naught over L del 2 v star over del x star square plus del 2 v star over del y star square. Now if you look at the scale v naught, remember we have defined h naught over L as epsilon. So this means v naught is u naught times epsilon. Okay, V naught is simply U naught times epsilon. So, this quantity we can write as, so I can write U naught square epsilon, and I can divide by H naught and again multiply by H naught to get this, and then this is del U star del V star by del X star, and then V naught is epsilon times U naught. So, this is simply epsilon square U naught square over H naught, V star del V star over del Y star, and then RHS is same. So, basically on the left hand side I can take epsilon U naught square or epsilon square U naught square over H naught, and inside the brackets we will have, and on the right hand side we have minus P naught over rho H naught. I can cancel this H naught, and then I can divide. So, there is this is V naught. So, I could have written this as epsilon times U naught, and I can divide everything by U naught square, and I will get epsilon square U star del V star over del X star plus V star del V star over del Y star equals minus P naught over rho U naught square epsilon nu over U naught H naught. Now, how do we get P naught? How do we obtain a physical scale of P naught, a physically relevant scale of pressure in this problem? How do we obtain that? How do we obtain a physically relevant scale of pressure?
Depends whether viscous or inertial forces are dominant.
No, no, this is the problem. I have given you a small geometry. I have given you geometry such that L and H naught are related by this. So, how can we determine the scale of pressure? How do we determine the scale of pressure? What would, so imagine a very thin slot. Why would you need a pressure difference to maintain some flow rate in that thin slot? So, consider a very straightforward case of this where this H is not varying in X, where the channel height or the slot height is not varying in X. In that case, why did we require pressure difference? To maintain a flow rate, to balance the viscous forces. Okay. So, that should give you an intuition. Okay, pressure needs to balance viscous forces here. Pressure will have to balance viscous forces here. It's a thin slot. So, how do we determine the scale of that viscous forces? How do we determine that scale? Hmm? So, if you think about a fluid, let us say if you think about a fluid blob or a fluid element of length L, okay, if you think about a fluid element of length L, then what you can say is that there is some viscous forces. So, there are viscous stresses that are acting on this guy, which are mu u naught over h naught. So, the scale of viscous stresses is mu u naught over h naught, right, because the velocity will be no slip here, it is no slip here, and it will be some velocity in the middle. So, there is a variation of velocity from 0 to u naught roughly over a length scale of h naught roughly. So, the scale of viscous stress is mu u naught over h naught, not mu u naught over L. not mu u naught over L. Okay. So you have this, and let us say you have pressure, and so this is P plus delta P and this is P. So for this fluid element, for this fluid element to be in steady flow, what you will say is that delta P, the force is to be balancing delta P over H naught, delta P over into H naught square equals mu u naught over H naught into L, and that gives us a pressure scale. So instead of delta P, the scale is for pressure, and that comes out to be mu u naught, just a second, sorry, into H naught, not into H square. So this comes out to be mu u naught L over H naught square. So the relevant pressure scale that we get is this. So this is the force balance in plane, okay, no z direction dimension I have considered. So pressure difference into area, which is H naught, and then the viscous stresses into area, which is L. Okay. So this is a very rough calculation. This is a very rough calculation, which is fine because we are trying to only get the scales. We are not deriving the full fields here. We are only trying to get the scales here. Okay. So for scales are rough, but a physically valid calculation is fine. Okay. So this calculation gives you a scale for pressure. So a scale for pressure is mu u naught L over H naught square. So P naught over rho u naught square, what do you get? It's simply mu u naught L over H naught square rho u naught square. What is this? So this is nu over u naught H naught times an L by H naught. Okay. So if I define a Reynolds number with the y direction length as REH as nu over u naught H, no sorry, u naught over nu, u naught H naught over nu, then this whole equation I can write as epsilon square u star del v star over del x star plus v star del v star over del y star. What is minus P naught over rho u naught square? This is 1 by REH. L by H naught is 1 by epsilon. So this is 1 by epsilon REH. So 1 by epsilon REH del P star over del Y star with a minus sign plus epsilon over REH del 2 V star over del X star square or Y star square plus epsilon square. Now what I can do is I can multiply this with epsilon times REH. So I can write on the left hand side this as epsilon cube times REH. This guy becomes 1 and this guy becomes epsilon square. So we know that epsilon is much less than 1, or we are trying to do, you can think of it like trying to do in the limit epsilon goes to 0. What we get here is that this is given if along with this, epsilon cube times REH is also, so if epsilon cube times REH is also much less than 1, then del P star over del Y star is order epsilon square plus, I mean, we usually write the leading order term here. So leading order is order epsilon square. So what we get here is that this is given. If this is the case, then del P star by del Y star is order this. So at leading order, or at order 1, del P star by del Y star is 0. At order 1, del P star by del Y star is 0, which means that at order 1, P is just a function of x. At order 1. Technically, this is true at order epsilon also, because we know del P star by del Y star is at max order epsilon square or smaller than that. Okay. So let us quickly do the non-dimensionalization of x momentum equation, and from there you will get, so you will get u naught square over L u star del u star over del x star, and then we'll have a u naught v naught over h naught. We know v naught over h naught is u naught by L, so again u naught square by L, which I can take outside. So let me take here again h naught square, and then I will have del 2 u star over del y star square plus epsilon square del 2 u star over del x star square. Okay. Now, if you use this scale of pressure, where is it? This guy. So, P naught over rho u naught square was simply 1 by epsilon REH. Okay. So, divide this by u naught square by L, you will have u star del u star over del x star plus v star del u star over del y star equals minus P naught over rho u naught square, which is minus 1 by epsilon REH, and here you will have nu by u naught h naught into L over h naught. So, this will again be 1 by epsilon REH del 2 u star over del y star square plus epsilon square del 2 u star over del x star square. And now multiply this whole equation by epsilon REH, and you will get this. Y star square plus epsilon square del 2 u star over del x star square. And now if we know epsilon is much less than 1, that is given to us. If epsilon REH is also much less than 1, then at order 1, the equation that we get is del 2 u star over del y star square minus del p star over del x star equals 0. Which one is the stricter assumption? Epsilon REH much less than 1 or epsilon cube REH much less than 1? Which one is the stricter assumption? So, if epsilon cube REH much less than 1 holds, then you don't know if this one will hold. But if this holds, this one will hold, right? So, the conditions under which these equations are valid are if epsilon REH is much less than 1 and epsilon is much less than 1. Okay, we will pick up from here after midterm. So, everything till now is a part of the